Thank you very much. Thank you to the Science Foundation Ireland and to the gallery, wonderful gallery here. Just been having a look around at it before. I've really got a whistle-stop tour through the different experiments. So I apologise if any of you are coming along thinking I'm going to say, well, there's this work going on and then there's this work and things like that. I'm not really going to do that. I'm just going to talk about what I think is most important, which is what I'm doing. And well, I think it's cool, so I'm just going to say what it is, and then maybe we can pick up on some of the more ethical points and questions as we go. So some of this, hope you'll know, and if you do fall asleep, well, wake up because there's a bit more coming on in a second. The first one, back to 1998, the first implant that I had, was partly trying to show what intelligent buildings could do, the fact that the building can start changing what it does when it knows who it is that's in the building. We used, back in 1998, radio frequency identification device technology, which was, then it was the sort of latest that you've got. Now I think RFID's around all the time. Here is a younger version of me with much darker hair. This is my GP, my doctor, and he was implanting in my left arm the RFID device, which is the thing on the right-hand side there, not the thing on the left-hand side. I mean, it's a very simple means of operation. Coils of wire in the doorway in my building with current passing through them. With that implanted, the current is induced in the coil. It just sends out a signal which identifies, in this case, identified me, to the computer in the building, so it opened doors for me, switched on lights, said hello, that sort of thing. And I got lots of criticism, who's ever going to want to have anything like that, which as you do, which is just for publicity, was some of the things, which was partially true. I mean, it was for publicity, but if you did something like this and you didn't publicise it, that would really be a bit silly. I mean, you need research income, and partly you publicise what you're doing, and if people like it, then it helps your research. So, yes, it was partly for publicity, not completely at all. But since then, has anybody got a cat or a dog with a chip implanted? Oh, thanks, one volunteer. Well, you can rest assured that this was fully tested on humans before your animal had it in. It's the same sort of technology, smaller, of course, not a big thing like this. A lot of people now have something like this. In the United States, biggest use of it is people who have diabetes. A lot of them now have implanted in them the sort of medication they need if they're rushed into hospital. So it's partly as a medical device to help people. Let's do something different. I'm going to bring you up to date with what some of my students, so I know this is more myself as a cyborg, but I get quite a few students who want to have an implant. So I'm going to show you some of the projects that they are actually doing. And I'm supposed to say don't try this at home, but I guess this is something if you want you can try at home, why not? I've got 3 students now, as part of their degree, the projects, have magnets implanted in their fingers. So this, in terms of human plus, if anybody wants to be a little bit human plus, this is something you could do, have magnets implanted. You notice the guy that does it, he's got tattoos on his arm. He goes by the name of Dr. Evil. Serious, which it does create problems because we have to get ethical approval in the university. So you can imagine these formal forms that we have to fill in, and then who's going to do it? Dr. Evil. It doesn't help the cause. This is Jowish, the first student that had it. You can see the magnets implanted in his fingers. This is an X-ray, obviously. He doesn't look like that normally. Hasn't eaten for several months or something like that. Here he is with, now you would see ultrasonics a number of times, sonar, ultrasonic sensors on the baseball cap. The output of those is used, you see on his finger, he's got a little coil of wire. As you pass current through the coil, it energizes the magnet. So the magnet starts vibrating, and linked up to the ultrasonic sensors, the closer an object comes to the sensors, the more the magnet vibrates. and the further an object is away, the magnet vibrates less. So essentially, he can feel in his finger how far objects are away. But you can link up to any other sensor, any sensory input. So I have a student this year, the same stimulation with the finger, but he's linked up to an infrared detector. Now, infrared is heat. So essentially what he can do is point and feel how hot an object is from a distance. So it's a remote detection of heat, which, of course, there are potentially immediate applications. If you think of, in the military domain, a soldier who's going into a building and he doesn't know whether there's anybody in there or not, it could be dangerous, they could shoot him, so he doesn't need to go into the building. With this, he can just put his finger around the corner and move it around. Ah, there's somebody over there, there's somebody over there. So that it has potential immediate uses. But really any sensory input you want to think of, you can convert in this sense. You can use substitution of the senses into this, the feeling, the inner touch. So, you know, if you want to, we look at the possibilities of scanning somebody in terms of an X-ray. Don't know how dangerous that would be, but you actually feel their bones, if you see what I mean. This is Ashley, who's, again, doing his undergraduate project with me. This is picking up on some work a guy called Paul Bakirita did. Officially, it's help of communication for somebody who is blind, but essentially it's communicating through the tongue. So it's a different form of communication. So the tongue is very, very sensitive. Both you've got more the taste buds at the front and then more texture at the back. And you can send patterns of signals on the electrodes. So either the person can detect different shapes, so it could be letters or all sorts of different shapes, but you can also send in directions. So in there you can, the person can centralize on where they're heading, and then a bit like a sat-nav, but a one that the person takes in their mouth, you can get them to go to the right and get them to go to the left and forwards and faster and slow down. So you can send instructions for the person to do different things via their tongue. So it's a different sensory route rather than putting more and more on the visual, which I think it tends to be a way normally to go. Now, I understand you had some stuff from Steve Potter in the exhibition a few weeks ago. And well, this is really extending on that. The brain, your brain, doesn't have to be where your body is. It just happens, evolution has come up with that for the moment. In the future, as a human plus, your brain can be somewhere completely different to your body. And this is one example of that. We're using a brain, biological brain, but a robot body. Now, just to get us into this, I've got a clip of some of the robots we actually use. This is a clip taken from a BBC programme called Inventions That Change the World. You'll see the first one is a robot head called Morgui, but it's more the robots with the wheels that are of interest to this particular presentation.
One of the AI community's leading lights is Professor Kevin Warwick.
Well, this is a robot head.
Dissatisfied with vacuum cleaners and robot dogs, Kevin's gone one stage further. His cyborg comes complete with
radar in its nose and an infrared top lip.
Is it intelligent?
Well, in a very limited way, I guess it is. It's sort of a basic instinct. What do I do with this information that I'm getting? How do I move? How do I operate if this signal is different?
So what's it doing now?
Well, if you clap your hands...
Oi, over here. Oh, it did it.
It's making basic decisions. All we've got it doing here is programmed to make basic decisions based on that sensory information that's coming in.
Getting the information in is nothing. That's like picking up a book. That's not an intelligent thing to do. Reading the book and knowing what the words mean, that's surely the intelligence.
Many machines can read books nowadays, but it means something different electronically to the machine as it would mean to a human.
Though the cyborg head does a reasonable job of sensing, it can't really interact with or explore its surroundings. It's fastened to its robot arm. And according to Kevin, it's only as intelligent as a dishwasher.
If that's a dishwasher,
Yes.
where are these in terms of, are they dolphins, chimps?
I think you'd have to say it's about the 50 to 100 brain cell area. So realistically, you're talking slugs and snails.
But a slug and a snail, they know to eat. They know. These things don't...
They have some innate abilities.
There's no self-preservation with that.
Well, we do have. The power supply, they don't have their own batteries. They each have power they're picking up from the floor here. That's where they're getting their energy. That's where they're getting their food
But
from.
if you turned off this section of the floor...
If we turn off
and
this
one
section,
was here,
they have a basic instinct to go and look for some power somewhere else.
They will
that. Keep going to do that until they find some.
So if I put him down...
It should go off looking...
So he'll have to go and look for power. And I got to tell him to do that.
No, it's an innate response for that robot. It's a basic thing of its life. Yeah, yeah.
No, his lights have come back on.
Lights are coming on.
So he's found
hopefully
power.
It's happy now that it's getting power. Away to go.
But these, then, are as intelligent as slugs.
It's different, but in terms of numbers of brain cells and that sort of thing, yeah, we have slugs. Probably you could say we're up to bees and wasps, the sort of tens of thousands of brain cells, is about as good as you can get. Yeah.
Bees and wasps.
Yeah.
Right.
Now, those robots we saw there have computers, microprocessors for brains. We can get them learning, we can get them communicating with each other, all sorts of fun things. But we've replaced the computers in the brains with biological brains. So the physical body is as we see on the right-hand side. The wheels to move around, which is good, it's pretty stable. But with the ultrasonic sensors, the same sort of sensors for sensory input. But instead of a computer, it's a biological neural network which is being grown on a multi-electrode array. The standard way of building this is in terms of rat neurons that are taken from rat embryos, separated using enzymes, and laid out. These rings are actually called Potter rings, after the guy, I think that you had some work from him the other week. They're really to stop the culture dehydrating, the brain dehydrating. So the neurons are laid out in there. Typically there's something like 100,000 neurons. They're fed with a pink liquid which has minerals and nutrients in it, very much like an energy drink that athletes have. After about 1 week, the neurons have linked up with each other and they're communicating big time with each other. So we connect up to the electrodes to stimulate the brain, link that up to the robot sensors, and then when the brain is stimulated, ding, 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 output from the brain which moves the wheels of the robot. So to give you some idea, the feedback loop, so there's no computer driving this robot at all, there's no human driving it, it has its own biological brain of typically 100,000 neurons. What it's supposed to do is move towards the wall and turn right, like that. But this is a baby robot. The brain is only about 2 weeks old. So you see it changes its mind, turns around, and bangs into the wall. And this is its early stages, a bit like a baby learning to walk. And we can see how it develops over the weeks. It's typically the brain is in the robot body for about 1 hour a day going through this procedure, and we can see under the microscope the neural connections strengthening that allow it to actually carry out this purely through the process of habitual learning. This is something called Hebbian learning. One neuron fires, stimulates another neuron, and in doing so it strengthens that pathway. So we can see this process of habitual learning, so that if we look at the same robot, now you see what it's doing there, bumping into the wall occasionally, getting it wrong, they're turning around when it shouldn't. You know, it's got a mind of its own. We'll now move forward to 2 months. So this is the same robot with the same brain after a couple of months. And in a sense, this is, I'm not supposed to say it's boring, but in a sense it is boring, as you'll see. Off it goes. Now, where we are with the research on this is, first of all, we're working with a group in Canada to grow the brain, to culture the brain in 3 dimensions, not 2 dimensions, and that increases the number of neurons to 30 million. Now, that's still some way from the human brain's 100 billion, but 30 million with the technology now. So that's what the size of the brain now is, 30 million. The other thing, we also have human neurons. I'd say human, we buy them from an American company, but it's the closest we can get to human neurons. So what we're looking at, sorry, that's the first anti-American joke of the day. Sorry for anybody who's from Chicago, Ian, sorry about that. Well, Chicago's not really part, anyway. So what we're looking at here are 30 million human neurons in a robot body. And clearly as the technology improves, so we're looking not just at 30 million, because it's a volume, the volume size increases very, very quickly. So there's all sorts of questions there of, is the brain conscious? Is it thinking for itself? Does it have a will of its own? Should it have rights? Because if we have animals with brains of 30 million neurons, we have to have licenses for them. You can't necessarily just kill it. It can be illegal and so on, dependent on what country you're in. So do we have to give the robot with a brain of that size, or can I just switch it off when I go home at night and it's no problem? Issues like that, robot rights, realistic. I think we'll pick up some up in the end. Okay, let's look something different. Rather than growing the brain like that, let's go straight to the human brain. Clearly we can pick up with electrodes on the outside what's going in the brain, but if we want to pick up exact signals in the brain and change what the brain is doing, we need electrodes into the brain. What you're going to see now is medical possibilities for Parkinson's disease, deep brain stimulation. If you've seen it before, okay, no problem, I'll pick up on what we're doing with it at the end. If you haven't seen it, this is a genuine person who has Parkinson's disease, received 2 electrodes in the central area of the brain, the subthalamic nucleus. You'll see, first of all, how the person is with Parkinson's disease, and then you'll see the assistant switch on the power packs. Now, some of you may wonder, if you're looking at Humanity Plus, even with Humanity, why we have lots of space here in the human body. There's not really much stuff here in terms of organs and things. Well, what this is for putting pieces of technology. It's a wonderful process of evolution, and here the power packs for the Parkinson stimulation are positioned here, and then there's wires underneath the skin go into the electrodes.
I'd like to show you in 2 minutes what was the status of Mr. Plasman when he was referred to us by his neurologist in Belgium. And you see him before surgery without drug, unable to stand up by himself. He's helped by Patricia Mouzin, who is a neurologist in our group. And he's not able to do anything of, as he will tell you, makes your life looking like normal. He's not able to walk. He has having dystonia, which are muscular contraction, deforming the different joints, and this is the best he could do without the drugs, with the help of people around him and maybe his wife and friends. He was referred because the drugs were not working anymore. He was not having any more improvement, and as he will tell you, he was just stuck to a wheelchair. This is after surgery. You see the tremor. We turn one of the 2 stimulators which were implanted with electrode into his subthalamic nucleus, which is a tiny part of the brain. And you see that in a few seconds, the stimulation induces the stop of the tremor. This is still visible on the other side. We will turn on the stimulator on the right side, and you will see something even more spectacular than that. You will see that the patient feels again free, and he reset himself in his chair in the position where he feels the most comfortable. he will obey Dr. Pollack in doing some tests, even if he feels that those tests are a little bit useless as compared to the feeling he has. He can do that almost normally on the right side, which should I do longer, as he say, and we'll show it on the other side. And then he will walk, he stood up alone. He's without the drug. You see him walking, turning. It was a few days before the Vienna meeting on movement disorder.
Now, we are working with surgeons at John Radcliffe Hospital in Oxford to take this a stage further. At the moment, the stimulator stimulates all the time, providing quite a hefty current, which uses up the power. And after about a couple of years, the person has to go back into hospital to have a power pack taken out, thrown away, and a new power pack put in place, a bit like replacing the batteries in a torch or something like that. But of course, this is quite traumatic for the patient, and they're actually operating to take the power packs out, so the potential for infection to get in. So what we're trying to do is to make the stimulator intelligent, so it only stimulates when it needs to stimulate. In order to do that, it needs to know when it needs to stimulate. So what we have, the electrodes that are implanted, we can also use to monitor the electrical activity in the brain. We feed that into an artificial intelligence system, which learns, first of all, to recognize when there are tremors or the muscle locking you get with Parkinson's disease, but secondly, to predict when it is going to happen before it happens, so that as long as the prediction is okay, the stimulator can then stimulate to stop the tremors before they even start, as it were, but it doesn't need to stimulate all the time. And with different patients, we now have the sort of accuracy that we're looking to try it out on actual patients, that the artificial intelligence system can predict from modeling effectively what's going on in the central area of the brain, can predict something like 20 seconds ahead before the tremors start. So if you like, the artificial intelligence system is outthinking what's going on in this particular part of the human brain, successfully, accurately. So it raises questions, okay, this is with Parkinson's disease, but how many other things could an artificial intelligence system outthink the human brain? So it knows what you're going to do before you know what you're going to do, is the point with that. And how many other things could you potentially use it for? So the last thing, a whistle-stop tour, rather than therapy, using technology to help someone with a problem, the possibility of enhancement. So it's linking human plus with human enhancement above the human norm, abilities that the normal human, whatever that means, doesn't have. As an example of the sort of line between the two that's not there, this is Campbell Aird, who lost his arm due to cancer, and he's been given this robot arm, but you'll see him flicking with his human hand, you'll see him flicking the switch which operates the robot hand and the robot arm, which seems a bit silly. Wouldn't it be better if he could control the robot hand directly from his brain? He didn't have to use his good hand, as it were, if I can call it that, to operate the robot hand. What this needs, though, is a bidirectional interface between his brain, between his nervous system, and the wires, and back the other way. And this is what my main line of research is all about. Great, if we have a successful interface, we can give somebody an artificial arm or an artificial leg. Fine, that's therapy. But we're talking then of brain signals, of neural signals, not just being on the nervous system, but being on wires. And as soon as we get signals on wires, we can clip onto them and send those signals wherever we want. So we can plug into the wires and plug the person's brain, the person's nervous system, into a network. So your body does not have to be where your brain is. Your body can be wherever the network takes you. So if you're happy to have an implant that links your nervous system to a computer bidirectionally, then your brain can directly control pieces of technology wherever you want the network connected up to. And you can sense all sorts of other things, infrared, ultraviolet. You don't have to limit to human senses, which are pretty poor. Sense all sorts of things wherever the network links you up to. So what have I done about that?
Now prepare yourselves for this. A British scientist has become the world's first bionic man.
It's true. Cybernetics Professor Kevin Warwick has had an implant attached to his nervous system. We'll have a look at it in a minute to discover exactly how the brain sends out signals controlling movement and even sensations such as pleasure and pain.
The secret operation involves surgically inserting an implant and cable into the left arm of Professor Kevin Warwick.
Well, the operation's been going about 10 minutes now. Spoken to Kevin, everything's going fine from his end, and the implant will shortly be about to go in.
The implant was fired onto a main nerve near the wrist. Wires from the implant were then threaded through a cable beneath the skin, exiting further up the arm to an electronic connector.
Effectively, what we've got is a link from my brain down the median nerve, through the wires and out to the connector. And then in the weeks ahead, we'll be putting on our radio transmitter receiver that we've developed at the university, and that'll be making the link by radio from my nervous system to the computer and back the other way.
This is what everyone hopes to see, nerve signals resulting from finger movement or even emotions. The medical aim is to help people who are paralysed, although some experts are unconvinced. But Professor Warwick is used to detractors, and experiments linking his nerves to a computer will begin soon. Sue Nelson, BBC News.
So, what actually happened? Well, it was a 2-hour neurosurgical operation. There were 4 neurosurgeons altogether involved. For them, it was a research project to see how to do it and so on. This is what was implanted in my nervous system. It's called the Utah array. That's where it comes from. Later also called the brain gate system, because there's a bit of a race going on. We beat the Americans to it, annoyed them a bit, so they changed the name of the device. We did use their technology, I have to say, so give them credit. So essentially each of these electrodes, well, the electrodes themselves about 2 micrometers across, which is the neurons typically, anything, nerve fibers, 2 to 20 micrometers. Is if you go tonight and dig out some of your brain cells, you'll see typically they're about 2 to 20 micrometers. If you find some that are 30 micrometers across, you don't win a prize or anything. You can get the bigger ones there. But typically 2 to 20, so the electrode tips about 2 micrometers across. The whole spike's about 1.5 millimeters though, which the nerve fibers, the median nerves, which is where these were fired, literally fired into, about 4 millimeters in diameter. So very, very small, but you've got about 10,000 nerve fibers. It's the main bunch of nerve fibers from your brain down to your hand, not to the little pinky, but the other fingers. And they also send signals back up the nerve fibers, so it's a bidirectional. So putting in like that, you've got signals a bit like listening into a telephone call. When you move your hand, you can pick up the neural signals and then get different pieces of technology to operate, but also we were sending signals into my nervous system that my brain had to learn to recognize. I saw some pictures of Stellark's arm upstairs. This is my own operation. The surgeons had to make 2 incisions and then push that tube down between the incisions so that array could be pushed down the tube. They then pulled the tube out, removed it, hammered the array into place. I had wires running up my arm, coming out to the little green connector. So the little gold contacts on the connector pad were essentially linked into my nervous system. So if I moved my hand, we could pick up neural signals on the gold contacts, send them into the computer to get pieces of technology to operate, but also we could send biphasic positive negative pulses into my nervous system by the same route that my brain learnt to recognize. So I've got just to finish off, got a little clip from Discovery TV to show some of the things that I could do.
One man in tune with technology is the world's first cyborg. Part man, part machine. Kevin Warwick, Cybernetics Professor at Reading University, England, took a leap into the future as long ago as 2002. For 3 months, a silicon chip was implanted into the nerves in his arm.
At that time, no human had had an implant of this type before.
It was a procedure that until then had only been tested on chickens.
Would the body reject it? Would it affect the way I moved or my sensory capabilities? I could have lost the use of my hand. Could it affect my brain? Ultimately, could have sent me crazy.
Kevin was plugged into a computer which monitored the nerve signals from his brain to his arm, receiving and transmitting them as radio waves. With the signals from his brain, Kevin could not only turn on lights, he could control a wheelchair. And from 5,000 kilometres away via the internet, he succeeded in getting a robot hand to mimic his own hand movements. His most impressive experiment involved his wife, Irena, also having a chip implanted in her arm.
The communication experiment between myself and Irena was vitally important to me. This was the highlight of the whole experiment.
Kevin wanted to discover if it was possible for his brain to receive and feel signals from Irena's brain.
When Irena first moved her hand, it actually felt like a charge running up my index finger. It was a phenomenal feeling. Literally, every time she moved, my brain received a signal. There we were communicating for the first time in the world, nervous system to nervous system.
It was the first time two people had electronically communicated by thought alone.
In the short term, we're going to see implants used to help people who are paralysed switch on lights, operate the TV, just by thinking about it.
In 30 years, he believes we'll all have chips in our brains.
But ultimately, having extra memory, having downloads from the computer, uploading from the brain. Earth is going to be controlled by cyborgs. Humans are going to be something of a subspecies.
We'll be half man, half machine, with super memory, super senses and superpowers.
I think quite clearly that's where we're going. Superhuman. So, I mean, hopefully there's nobody here wants to just stay as an ordinary human. I mean, you're all here with the gallery as well to become a human plus. But hopefully this has given you some ideas, small ways like the magnets being implanted, giving you a few different sensory feelings. Or, ultimately, I'm sure you'll be wanting to go for the brain implant to be able to communicate directly brain to brain. Because when you think about it, how we communicate as humans is vitally important to our intelligence and our intellectual makeup. Yet at the moment, our communication is absolutely pathetic in comparison with how technology communicates. We have all sorts of complex electrochemical signals in our brains, thoughts, images, ideas, emotions, feelings, etc. And if we want to communicate those to somebody else, presently we convert those highly complex electrochemical signals into trivial coded mechanical pressure waves. This is what speech is. It's a trivial coded serial. Can you believe we still communicate serially? And somebody's ears will pick those signals up, the mechanical signals, and convert them back to electrochemical signals. Of course, even if you've been married for 40 or 50 years, you still have no idea what it is that your husband or wife is trying to tell you. So the possibility of communicating via a network in parallel, directly, brain to brain, opens up the possibilities for communication enormously. That in the future, as a human plus, as a cyborg, we will be able to communicate in terms of feelings, colours, images, emotions, much, much richer form of communication. So again, if you want to be an ordinary human and communicate in this old-fashioned, what we should be getting rid of form of communication, or in the much richer form, then Human Plus is the way to go. Thank you very much.
Professor Kevin Warwick, thanks very much for that. There is a microphone, I think, going around, so if anyone has any questions, just raise your hand and we'll deal with them as they come. But we'll start off, if you don't mind, just having a quick chat, Kevin.
Yes.
I find this such a fascinating field.
Me too.
But I want to start off talking about your quote there, that human beings will be a subspecies. Give us some more information. What do you mean by a subspecies?
Well, I mean, first point, I see intelligence as the key. If you compare humans with other creatures on Earth, I know there are some locusts maybe are more numerous, but in terms of our position on Earth, we're in a pretty cool position as humans, and we do lots and lots of things and so on. But you're comparing us with other creatures. I mean, this is pure Nietzschean philosophy, really. Compare us with cows or sheep or even animals that are in zoos. We're relatively speaking, we're quite dominant. What do we do, whether we like it or not? We keep them as pets, maybe. We eat them. We keep them in zoos if they're lucky. You know, they're not in such a wonderful position. So, why is that? Well, it's our intellectual abilities that give us that position. So, if we're looking at now human plus superhumans with intellectual abilities for communication, different sensory input, the possibility for thinking in more dimensions, extremely powerful intellectually, how are they going to regard humans who are, as we see now? If the human says, you shouldn't do this, this is just silly noises. Just like now, if a cow came in the back of the room, moo, 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 we're not going to say, yeah, that's a wonderful idea. Yeah, we'll go ahead, we'll do that. We're going to get out. What's it doing in here? So that's really how life for humans are going to be. They go to the human plus the cyborg. In the multi-dimensional thinking will be effectively get them out of here. So if a human in the future, if you're lucky, you might be a pet. But that's the really lucky ones will end up in that.
You talk about extending our memory and intelligence, and this is something that I'm a little worried about, that you say in the next 30 years we'll be able to upload and download via the internet. And a lot of people, Ray Kurzweil is one of them, believe that this is something that will happen very soon, that we'll be able to connect our brains and store memories on the internet. Aren't there serious implications with something like that? Don't we become the Borg? How do we remain individual if we all have access to the same information?
Yeah, no, I think the Borg was perhaps putting a more negative spin on it. I mean, I see the more, well, to say the least, as science...
You've got some bad press.
As science fiction does. I mean, if you imagine now your brain is linked to a network and lots of other brains linked in there, so you've still got partially your individuality, you're still you, but you can enhance the way you communicate, as we've been describing. You can get hold of the memory base. Essentially, actually remembering anything in the human brain really is a complete waste of time. The human brain is not very good at doing that in comparison with computers. We can see all sorts of visual memories and so on and so forth. So why not outsource the memory of the human brain, get it done within the network that is then a shared memory? So I think there's much more of a collective spirit, that we can understand all the others who are connected into the network much more. So, I mean, at the moment, if somebody here in the audience says yes or no, we don't really know what they mean by that. But if we can experience more emotional input and more shared memory, we get to know what they do mean by that much more. It's much more an intimate form of communication. So I see it much more positively that as a part of the network, as part of the Borg, that you have shared experience, shared feelings to an extent. You've still got your individuality to an extent, but much more of a collective whole.
You had that implant in your arm for just 3 months. Firstly, why just 3 months? And secondly, when you were linked up to Arena, do you think that if you'd had more time connected together, that you would have been able to make more out of the impulses that you were getting into your brain, the jolts?
Yeah, I mean, I'll answer the second question first. Yeah, it was a difficult thing. Of course, for everything that I talked about, we have to have ethical approval. And getting ethical approval from the university, from the hospital authorities, and so on, which we've done. So in case anyone is spy from the University of Reading saying, make sure you say you've got ethical approval, we did. But getting ethical approval to do my experiment, which was pushing the boundaries somewhat, I have to say. Having an implant in your nervous system is not something you do every day. But part of it was to see how my body would react. Would there, completely the body, would there be any problems and so on. So to get the same implant for the same time for Irena was difficult from an ethical point of view, but we did get ethical approval for the implant, the electrodes that she had. And we did communicate in the way, which was great. I mean, that was a fantastic feeling to actually, when she closed her hand, my brain received a pulse. So when she went like that, my brain received 2 pulses, which was a wonderful experience to actually do that and know, no one's done this before. If we had been able to connect up for longer, yes, we wanted to look at a whole range of things, particularly more on the emotional side, because you can pick up on what I would describe as the more physical emotions, anger, shock. You can measure on the nervous system, and hence we wanted, particularly excitement, we wanted to look at sharing excitement together. So Irena would know if I was getting very excited, she would know it, or if I'm getting, excited. But I mean, if for anybody who's not sure, doesn't believe me on that, if we just take one experiment, which if I was to go, like that, so the point is, if I was measuring your nervous system, I mean, that was an example of shock, more physical emotion. Clearly, I hope everyone would agree, we could clearly see this person is shocked. The same for anger and stress. Ross Pickard at MIT is picking up signals to do with anger and stress. Excitement, if you're calm and relaxed, anybody into meditation knows the signals are very different as to when you're excited about something. So it's not difficult to pick up signals that indicate feelings, and that was something that we wanted to do, which we didn't have time to do. 3 months, it was a fair time, actually, to have an implant. I was like a walking laboratory for 3 months. We were in the lab every day. Typically it took us about 2 weeks to get a particular experiment sorted out. Some were ongoing, like getting my brain to learn to recognize things. The robot hand experiment, I had to go to New York, to Columbia University. We plugged my nervous system into the internet, so there was a live connection linked to the robot hand back in Reading, in England, and then signals back the other way. So I was moving my hand in New York, my neural signals went across the internet, moved the robot hand. When that gripped an object, signals were sent back across the internet that my brain could recognize. But it all took a lot of organization to make that happen. And, 2 weeks, even just booking up flights and things like that takes time. And then we moved on to the next one. So 3 months was a very, very busy time, but we wanted also to see what happens when the implant comes out. And what we found was that the body had grown tissue around the implant, actually pulling it into place. So rather than trying to reject it, it had done the opposite.
So you could have actually kept it in?
Could have kept it in for longer. One of the negatives, the wires came out of my arm here. You see 2 scars. There's the one where the implant was in place, wires up there, and then this is where the wires came out. And at this point, I had to go into the local sort of not the hospital, but I had a nurse checking up on me every week to make sure there was no infection. And really the wires were being moved around like this, and they were breaking at this point. So at the end of the 3 months, we only had about 3 connections left because the wires were breaking here. I mean, the wires actually implanted were fine. So if we'd have left it in for a lot longer, it probably wouldn't have been doing anything. So it was about the right time to come out.
We'll talk about ethics in a bit. Does anyone have any questions? This gentleman here?
Just in reference to 2 of the projects that was shown there. The one where the wheels, the robots and wheels, had learned, or the biological brain, if you like, not an artificial neural network, but an actual neural network.
Yes,
okay?
That's right.
So that and the Parkinson's patient, where you were trying to embed technology there to help them, and there was power issues. Are people looking at actually bypassing the technology, in other words, growing biological technology to enhance existing biology?
Well, I mean, with the brain, the rat brain robot, if you like, that's exactly what we're trying to do, is to, if you like, we've got a brain that is growing, and then as it grows, we've got the possibility of enhancing it by adding neurons or adding stem cells, which then function as neurons. But the point is, where do we add them? So one of the issues is, in terms of understanding how this mini brain is operating, one of the big drives is in terms of memories, how a memory is actually formalized in the brain, how the neurons connected, which we have no idea about, to be honest, in general. And hence with things like Alzheimer's disease, dementia, ultimately, could we be able to inject new neurons at the right time into the brain? I mean, this is very, very speculative, but you have to start somewhere. We need to know where to inject, how do we get them connected up. One big plus on this is that neurons like to communicate. Within about 20 minutes of laying these dissociated neurons down on the culture, on the electrode array, they are sending out what look like tentacles and start to try and connect up with other neurons. They ultimately become the dendrites and the axons. But first of all, they're just... So what we're trying to do is to see how can we do that, so that ultimately maybe we could go to the Parkinson's disease and other neurological problems. With Parkinson's disease, the big advantage is we know roughly where you can stimulate, so possibly we could put neurons into that area, but it might not be the right area. So trying to figure out when we can pick up signals from there, where the pathway is to bring about the tremors and the muscle locking. So it might be a different position, but yes, I think ultimately injecting neurons, injecting stem cells potentially is the way to go. But it is a long way out.
Right. Okay, right. Thank you. Thank you.
Another question there? Yep.
Sorry, I was hidden here. You talk, with reference to the Human Plus project, you talk about vastly increasing the range of inputs that the human brain is going to be taking in, whether it be UV, infrared, or what really amounts to electronic telepathy. Do you have any concerns that there's sort of a hard limit to the number of inputs that the human brain can handle at any one time? I mean, evolutionarily, as our visual senses have developed, our olfactory senses have sort of degenerated. Now, maybe that's an artifact, but do you have any concerns that, you bombard the brain with all these new senses and these new inputs, that you might simply kind of overload the senses a bit?
Yeah, well, I do have concerns, and even what we did essentially we grabbed hold of some nerve fibers, and I had to learn to recognize pulses on them. So it was learning a new input, which was relatively trivial, but as various neurologists said afterwards, you crazy, what are you doing there? I mean, it could have had a detriment. The brain could have said, I don't want to know. It could have had a negative effect. So there are concerns there. It's pushing the envelope. I think in our favour, the brain, even if you're an old guy like me, the brain is very plastic. It's still there to adapt. And we see that if somebody has a stroke, the other parts of the brain can suddenly pick up and learn relatively quickly, within a few weeks or months, to do things that they've never done before. They can take over duties, and hence the person can, over a period of time, learn to do things. Different neurons that were doing something else now reclassified, they're doing something completely different. So the brain is quite plastic, that it can take on board new senses. I think also the brain is quite mercenary. Now, what I mean by that, as you were saying, that with the vision it's become more and more powerful, and the sense of smell and taste, perhaps even more so, has become less well defined than perhaps it was years ago. And therefore, if we feed new sensory input in, the brain again will probably say, well, yeah, I like this is useful, but if it's not useful, it maybe won't be of any interest. Like the remote sense of heat. It from a technological point of view, this is fun, let's try it, we can try it. But whether it would be too much use to the human, some humans maybe yes, and others maybe not so much. So, but we can try and see and find out. But there are concerns, obviously, and it may be different with different people, that all it takes for one person is, you give them an infrared sense and it's too much for the brain. What will happen then, we don't know.
You talked about that sense of being able to detect heat using infrared. Is there a concern that a lot of these sort of projects, and a lot of projects that are involved in the development of robotics and the interface of biology and technology are being developed by the military? DARPA is very heavily investing in America in this sort of technologies. And I remember reading about a soldier that had a bionic eye that allowed him to see in the dark out of one eye. Is there any concern as someone working in the field of cybernetics that the money is coming from the army and therefore what are they going to do with it?
Well, I mean, one of the brain gate that I showed, the Utah array, the only other person that I'm aware of that has put that in a human is John Donahue in Rhode Island, Providence, Rhode Island. And that was if you see, Matt Nagel was the first to have it in his cortex. That was about 3 years after we did it. And I think he's put it in another patient, but we're not sure how well it's gone, so we don't know at the moment. But he's funded directly by DARPA, which in a competition, I mean, he literally got billions of dollars, enormous amount of funding that's gone in using that implant in people. We haven't got any of that funding, so typically we've done it on a shoestring and so on, but still beat them to it in that. There are concerns as to what it's going to be used for. And again, John, as with another, Miguel Nicolelis is a good example where they've got lots of funding in the same sort of area. They are very closed as to how they would talk about what's going on. Now, if you had John or Miguel talking here now, they would not answer a lot of questions. Some of the questions, like we've just gone, they will not go there because their funding restricts what they can say and how they can talk about it. I am completely open, which I hope, so we can discuss it and say this, it could do this, it could do that, positives, negatives. With any military funding, it's all it's all very complex. Cool. If the military funding pushes the technology can be used for all sorts of things. So isn't that a good thing? If the military is our military, isn't that a good thing? I think with any technology, whoever funds it, anything, it can get used for good or bad. It depends on how you define good or bad. Any scientist that is developing anything, even equations, could get picked up and used in a negative way as far as somebody's concerned. So as any scientist, you live with it, and hopefully I'm, as others, open enough to say, well, could be used for good, could be used for bad. I mean, some people have said about Albert Einstein that if he had known what he was going to do, he wouldn't have done it. Complete load of rubbish. I mean, this is just to paint Einstein as some angelic figure. He's not. He was a regular guy. He was a scientist. He knew that what he was doing could have been used for good. Could have been. He was a clever guy. I mean, if he said, I didn't realise that means he's stupid. Well, one thing that Einstein was stupid. He knew it could have been used for good or bad, but he didn't take his Nobel Prize back afterwards. Oh no. He did what he did, and he knew it was possibly good, possibly bad. And I think any scientist is in that position.
How are we doing for time there, guys? Yeah, we're okay. We'll take some more questions then. This gentleman here.
Hi. When you talk about memory interfaces, something like that, implants to augment memory or cognitive ability, there's a huge amount of breakthroughs that are needed in understanding the semantics of what happens in the brain. Before we can even talk about doing stuff like that. Are you optimistic about those? And do you have any ideas from what sort of disciplines or fields you see those coming from?
Yeah, I mean, I agree with you completely. It's a long... I don't know, before we can talk about it, I think we can talk about it, but to actually, we're going to conduct an experiment now, yes, it's very, very difficult. We need to understand a lot of the basics of what's going on in memory and so on. I mean, where we're at... Yes, in terms of the little model brains, we can perhaps start to understand what the neurons are doing, but how they communicate if you're trying to recall a memory, Are there some neurons controlling that recall? What's important about the pathways? Where is the memory stored? We don't really have much of an idea at all. Yet, with electrodes implanted into the brain, different signals into the electrodes to stimulate the electrodes at different points can get the person to recall memories. The experimentation that's been conducted, pressing the button, oh yeah, I remember when I was a young girl or boy, whatever it is, and doing this in the fields and walking through. Or I remember a sporting event when Rangers beat Celtic or Celtic beat whatever it was. So there is some progress in terms of electrodes put in particular regions of the brain that are stimulated with different currents and voltages, that the patient or the person starts to recall events. I mean, it's not the sort of thing that a person who does not have a neurological problem would, though, go through, unless they're a scientist, I guess. So most of the results are with people that have Parkinson's disease or epilepsy or depression or Tourette's syndrome, where some experimentation has gone on. So it's very, very limited. We know with appropriate electronic stimulation of the brain at different points, memories can be recalled. Going the next step to storing those memories externally, or in a controlled fashion bringing about memories or downloading memories, is what you're saying. It's difficult to start talking about it in a practical, realistic way at the moment. So there's a lot to learn, but I can't see why, if we're looking 10, 15 years, surely we would have got some way down that road by then.
There's a lady here.
Hi, I just have a question about the way you were saying the robots were turning right. Did you program the robots to turn right, or did they just decide themselves to turn right?
The answer's a bit in between the two. What we do after about 1 week, the electrodes on the outside, we pull round. So we will stimulate on one of the electrodes and see where there appears to be a response on another of the electrodes. So it's like stimulation, here's a response, reasonably repetitive. So it might be we stimulate on electrode 27 and on electrode 63, 25% of the time we get a response. And let's use that. So this is effectively how the brain has grown. We now use that, connected up to the robot body, which is what you see. So you get the stimulation, and 25% of the time the robot will turn right. The other 75% of the time it crashes or does something different. But it will keep doing that. So as long as the hand of God, if I can say that, comes in, moves the robot back into place, and off the robot goes, and as long as it does respond to that stimulation 25% of the time, after 2 weeks, that 25% has become 35%. And after 3 weeks, it's become 45%, purely through the habit of doing it. So we don't program, we take the way it's grown to a certain extent and enhance that. Keep it going through that particular procedure. So it goes through it, it does it, which strengthens the possibility that will happen. You go through it, it does it, it strengthens it more, and it strengthens it more. Every time it does that particular action, it becomes more likely to do it in the future, which is this habitual learning. Anytime we do something, whatever it is, we become more likely to do it in the future. I mean, usually we do all sorts of different things, but it's the sort of thing, if you drive a particular route, sometimes you feel, I didn't even think about it, I've gone this route. That is, we're doing it habitually, and it's the same process. But here we can take that to an extreme. We can apply chemicals to different regions of the brain, either to restrict growth or to enhance growth. So chemically, we can reinforce things that we like what it's doing, or cut back on things that we don't like what it's doing. So we can reward and punish chemically, but at the moment, electrically, as far as we know, it's not possible. We can't apply an electrical pulse and the brain, that's a good idea, I'll do that more. If we do figure out how to do that, we'll be using it on our students immediately, that we can, right, this is a good thing. Yeah, I like that. So.
I wanted to ask you about, you were talking about using human neurons and interfacing them with technology. There's a book called The Immortal Life of Henrietta Lacks. I don't know if you've read it, but it's about a woman called Henrietta Lacks who had cancer cells taken from her,
yes.
and they were grown in a lab, and now they're HeLa cells, they're used in biology across the world. And her cells became commercialized, and you can buy lots of HeLa products. It cost a lot of money. When the family found out, they flipped the lid, because they had no idea, A, that this was possible, and B, that their mother was alive somehow in these cells. When you create the rat robots or the technology that's interfacing with human neurons, where does life begin? You were talking a little bit about the ethics there.
Yeah.
What are your thoughts on that? Does a robot that's powered by human neurons have a life? Does it have rights? Does it have an identity?
Well, I mean, first of all, on cancer cells, particularly tumours, neuroblastomas, these are tough cells. I mean, normally the cells have to be kept, neurons have to be kept in an incubator at about 37 degrees centigrade. We found with the rat neurons, you can actually vary the temperature a bit, and they're relatively tough. But with the human neurons, they're quite volatile, and if you don't have the temperature right. But with neuroblastomas, with cancer cells, I mean, literally, we've thrown them away, and next day pulled them out of the bin. They're still alive. You know, it's very difficult. Never mind the wrong temperature and the wrong environment, can be very difficult to kill them, which is good from a research point. I mean, it's bad if you've got a tumour or something, it's difficult to kill them. But in the laboratory, even students can, students can kill anything. But with the neuroblastomas, even students have difficulty killing these things. So they're tough. And if we can actually use them for a positive, which is the sort of thing you're describing, they can be a very positive source, because we can get them learning and enhancing, doing all sorts of things. Ethically, with human neurons, the big positive is that any results we get with the human brain then have a much more immediate impact, as far as if we can get the results here, then they mean more as far as medical application immediately. Tipu Aziz, who is the consultant neurosurgeon we work with mainly at Oxford, any rat neurons he doesn't regard with any. There's nothing like the human brain, therefore the results are not particularly relevant. I mean, he works with monkeys, which we don't do, but he does for Parkinson's disease. So monkey brain is roughly similar to the human brain, but the human neurons, if we get results with them, he sees as being then relevant to the human brain. But ethically there are questions, yes. I mean, we buy them from a company, so literally we phone up and the neurons appear next day. But they are, we understand, from abortions, but potentially they could be taken, as you're describing, from people later in life, or donations. There's all sorts of possibilities. So ethically there are issues, yeah. I mean, particularly, is it alive? I've had the biology professor at Reading came to me when he found out what we're doing. He said, yeah, technically your robots are alive by the definitions of life the brain life, death, definitions that I have, which they are. The cells are growing, they're alive, they're the way they communicate is due to a life. Okay, they have a physical robot body, but then a lot of people, you have somebody who's paralysed, they're in a wheelchair, so partially, or Amy Mullins, we see her pictures up there with her carbon fibre legs. She's alive, but she has partially a robot body. Well, how far do you take that? So if it's to the extreme where you just have a live biological brain, but the whole of the body is then robot, but it's alive as far as I'm concerned.
Something for you to ponder on. I suppose we have to let Michael John ask a question. He sort of runs things around here. What, Michael John?
What's your next enhancement?
I think for me personally, the students you can try this, it's great fun. The students with magnets implanted really are having, scientifically it's great fun at the moment. This used to be something a lot of body modification people did. There might be some body mod people here. So it's not an area of science with a long scientific track record, and yet this sensory substitution is phenomenal. The students, they can zing, zing, zing and detect distance. It's really good. So it's right at the start of the whole area. So I quite fancy having a go for that myself. But for me, the big one is the brain implant, because communication, brain to brain, I would like to experience. It is quite dangerous, and I've said I'm not going to do it before I'm 60, which gives me another 3-4 years before I go for it. But we need to find out the exact position. There's still work we need to do.
Will you get your wife to do that one as well?
She's shaking her head. I think for that, she has decided that one is a bit too dangerous, which it is. I mean, we're talking about how the brain might react. We don't really know. The only 2 people that I'm aware of in the scientific literature that have had implants of this type, well, there's 3 people that have had this type of implant, of which I'm one. The other 2 are not alive now. That is not because of the implant, it's because they were ill and they had, but they haven't been able to live to tell the tale for too long. So it is a dangerous game, but I would like to experience, and the communication side of things to me is vitally important. And the only way to prove that it works, to show that it works, is to go for it and experience it.
Well, I think that's about it. I think we've run out of time. It's been fascinating speaking to you. Really appreciate your time.
Cheers. Nice to speak to you.
Thank you very much.
Cheers.
Professor Kevin Warwick.